Hello and welcome to this VLDB presentation on normalizing property graphs. My name is Sebastian Link. This is joint work with Philip Skavantzos. You can see the outline of a talk presented in form of a property graph itself with nodes, labels, identifiers, and edges between them. Let's start with the motivation. We want to achieve a framework where we can apply classical normalization theory to property graph models. So the real question is here how we can group properties of nodes intelligently so they benefit data management. For example, in the form of data integrity, where we can comply with business rules of the underlying domain in a way that leads to efficient updates by reducing the number of data redundant value occurrences. If we can enforce functional dependencies by keys, that will allow us to introduce unique indices and therefore also speed up queries. So these would be classical benefits. But in the property graph model, we have several challenges. For example, how can we normalize without a schema? How can we address underlying requirements in a flexible way? Graph data is semi-structured, including missing properties. So how can we achieve robust results in such a framework? In summary, how can we actually transfer the deep relational design theory to such a property graph model? To illustrate this on a case study, we look at people that attend events. The events have properties such as name, company, venue, and time, as illustrated in the property graph in there. Constraints then should also come together with the set of labels and the set of properties to which they actually apply. So alongside typical uniqueness constraints and functional dependencies, we also want to declare which labels and properties need to exist for the nodes to check. So if a node does miss a label or does miss a property, then they are not part of all the nodes which need to be checked for the constraint to hold. As an example that we use in here, we can see how the event nodes are part of the constraints. We can see how the properties are defined that need to be part of the constraint and that need to be existent on the nodes that we actually consider for the constraints to hold. And then we have typically our uniqueness constraints and our functional dependencies as from the classical case. This leads to problems with data redundancy for the functional dependency in there where the name determines the company on all those nodes labeled event and for which the properties name and company actually exist. If we change any single value of cactus in the property graph in there, that will result in a violation of that constraint. That may lead to inconsistency and inefficiency because we might not be able to update all the redundant occurrences in there, leading to inconsistencies. And if we want to update all of them consistently, then we have to find all of them, so that may lead to inefficiencies of updates. At the same time, having to locate all the redundant data value occurrences in a query will typically slow them down as well because we cannot apply unique constraints. So let's have a look at our main contributions. So the first one are the graph tailored constraints, tailored to sets of labels and properties. So these encompass uniqueness constraints and functional dependencies. They're able to therefore express requirements for labels and properties as well. And it leads to a robust approach to handle missing properties as well. The underlying implication problem is decidable in linear time, although the problem is p-time complete. We were able to generalize all the classical normal forms like third normal form and Boyce-Codd normal form and tailor them flexibly to a given set of labels and set of properties. The Boyce-Codd normal form, just like in the classical case, characterizes redundancy-free normal forms, whereas the third normal form minimizes the sources of data redundancy across all decompositions that preserve all the functional dependencies. So in fact, all the results from the relational theory can be generalized successfully. In form of the normalization, we are given a property graph G that is satisfying a set of graph-tailored uniqueness constraints and functional dependencies. And now we would like to normalize this with respect to a given set of labels L and a given set of properties P. And this is what we're achieving in the output. We're achieving a normalized property graph that satisfies a normalized set of constraints, which represents a lossless preserving decomposition of the given input set of constraints into third normal form, which is guaranteed, but it is in Boyce-Codd normal form with respect to the set of labels and properties whenever such a Boyce-Codd normal form actually exists. That is FD preserving. In our experiments, we show that constraints capture data redundancy in real-world property graphs, and that our graph normalization process actually eliminates or minimizes, respectively, data redundancy proportionally to the reduction of update overheads and speed up of queries such as aggregate queries, for example. Let's illustrate this now on a specific example. So we have our set of constraints given with respect now to set L of labels, which is the event node, and the set of properties NCTV. We would now like to normalize this input set. We can convert this based on the given L and P into a classical set of functional dependencies. And this is already in third normal form over this relation schema in here, NCTV, which is the given set of properties up there. So the question is here, does a Boyce-Codd normal form decomposition that is FD preserving exist? And that's the case. It's given up in here. This then can be converted back into a set of graph-tailored uniqueness constraints and functional dependencies. Here we only require uniqueness constraints because it is actually in FD preserving Boyce-Codd normal form with respect to the given label set and property set. Now we can apply this to our given property graph, and the way it's done is that we look at the elements of the decomposition and then project the nodes accordingly. So for example, if we project to name and company, we can see on both nodes we have the same projection. It's value equivalent. So therefore we only get one node in the normalized property graph with edges back to the original nodes that the projection results from now. All right, so and this is done accordingly to the other elements of the decomposition, which works very nicely. But here the projections are different on the nodes, so therefore we also obtain different nodes in the normalized property graph. If we then look at the resulting constraint sets, we can see here that all the functional dependencies can be enforced by uniqueness constraints, which makes it in Boyce-Codd normal form, and it's FD preserving. Here's the example where the name actually is unique within this particular context. So that's an illustration how property graph normalization works. Let's have a look now at the experiments. So for that, we looked at real-world property graphs like Northwind and Offshore. Offshore is quite a famous set from the Panama Papers. Here we focused on particular nodes with the label entity. So there are lots of nodes still with that particular label. And also the nodes exhibit various properties in here. So the percentage of these nodes is approximately 1/4 in this case. We mined functional dependencies and uniqueness constraints with this label and these properties, and this led to these different numbers in here. The functional dependency caused an average redundancy of 48,000. So that's of course an incredible number, and it highly motivates the research that we have conducted. So we could then, for example, classify the graph functional dependencies that we mined according to the number of properties that they actually exhibit, and that leads to this distribution, if you like. And here you can see the number of graph functional dependencies with these, with this cardinality of properties. It's trivial if the properties only contain those that are present in the functional dependency itself, no additional properties. So you can see that there are also a lot of others in there as well. Here are the top ranked one according to the number of redundant data values that they cause. And here int denotes actually the maximum number of a single property value, how often it occurs in there. And you can see that these numbers are quite staggering. So again, normalizing here should help a lot with the issues that we've mentioned before. Then what is the normalization effort that we need to put in? So for that, we looked at real-world properties and constraints on this offshore data set. P3 here is actually the union of P1 and P2. They have different graph functional dependencies that we extracted from this set. And here's the number of redundant data value occurrences that we eliminated by this process. Here is the number of database hits that were required by the normalization effort, which is proportional in the number of redundant data value occurrences as well. And here's the size of the output decomposition, if you like. So what you can see here is that the database hits are proportional to the volume of redundancy that has essentially been eliminated. Here's a simple illustration on a property graph with different entities. They have a property called countries. So we could have, for example, these 3 different countries in there, and it turns out that Croatia is the country, is the location of these 3 entities in here. But by pulling it out, we actually reduce the redundancy for this particular country. And of course, we can do this for any country. So you can directly see what normalization here actually means and how much is saved by doing that. You can then look at the update operations and query operations and what the impact is on those. It's quite staggering to see the effect, even just by introducing an index on the left-hand side of functional dependencies. We already save an order of magnitude in update operations. But then when we normalize, without even introducing indices, we save an incredible amount of magnitudes of orders. And then if we normalize further, we actually achieve the optimum result where we only need one axis, which is, of course, natural with having eliminated all the data redundancy in there. This is also representative in the times that we have achieved in here for these operations in both Neo4j, but also on AWS online. Similar results hold for queries to smaller amount, of course, but still similar here for aggregation queries, what we've seen, and also for these queries and the times. So those were the experiments. So just to summarize now, so we've delivered a first approach to normalizing property graphs, despite many challenges present, like not having a schema, needing to be flexible in terms of the requirements of applications, having to deliver robust results under different interpretations of missing properties, for example, and wanting to generalize the rich achievements from relational databases. So our graph tailored constraints can actually express application-specific requirements for node labels and properties. They are robust under different interpretations of missing property values, and they enable us to transfer the rich relational theory to property graph models. And our algorithms can eliminate and minimize data redundancy that's proportional to the reduction of overheads for update maintenance and the speed up of aggregate queries. Here are classical references: third normal form, Boyce Codd normal form, dependencies for property graphs, and so on. And now we can come back to the property graph for our original talk structure. Of course, we could now introduce properties, namely the status of having processed these topics. We are now done with all of them. That, of course, introduces a new functional dependency for nodes that are labeled with topic and have the property status, the status is actually constant. So according to our normalization theory, we should pull out the status, put it into a new node, and then having achieved a normalized talk. Thank you very much for listening.